Hi, my name is Pradyumna Rao, and I am presenting our capstone project on behalf of Group S2025. Our project was object imaging using millimeter wave sensors. My group members are Su-Min Kwan, Matthew Varghese, and Thomas Tran. Our advisors in this project were Dr. Ying Chen, Song Yang, and Jin Yang. So our basic motivations for this project were that the need for public safety is constantly increasing, and with traditional methods such as metal detectors, they can often be too expensive, cumbersome, and just not practical in certain situations. So they're also needing constant supervision. Someone has to be operating them. So we wanted to find a way to circumvent this. And traditional methods use Wi-Fi signals, and they can be not as accurate. But for this project, we wanted to test millimeter wave or radar technology and see if that could be a viable alternative to detecting, for example, bombs in public stadiums. So this is a common public safety situation where this could be applied. We want to use the millimeter wave sensors to identify different types of objects such as metal, liquid, plastic, cardboard, etc. We also want to classify these objects using different machine learning algorithms, such as support vector machines or logistic regression. And we can also leverage these signals to detect both distance and angle of the object from the sensor, and this will effectively allow us to image the object or get an idea of what it looks like and get a depth perception and that sort of information. Here we have a simple flowchart detailing how each sample can be processed. For example, here we have a cardboard box. The millimeter wave sensor will capture the data on the box. Then we will pre-process that data. Then we also process that data, and that allows us to do two things. One, it allows us to use machine learning classification to identify that it is indeed a box and not, for example, a cylinder. We can also compute the distance and angle for imaging, and in this case, that would give us a distance of 1 meter. So some of the challenges we faced in this project are that it can often be difficult to image complex structured objects, such as water bottles which have grooves and plants which have a lot of irregularities or holes. These kind of irregularities can often be tricky when it comes to the millimeter wave sensor. So we also needed to find the best pre-processing step for the data. And of course, the COVID-19 pandemic adversely affected all of the capstone groups, and we were no exception to this. We needed time in the lab, but this became impractical because we had to change to the remote project, and we didn't have access to the sensor for actual data collection, and we also had very limited objects for classifications. So our contribution for this capstone project is that we trained the machine learning model based on the data that we do have. We only have it for 2 different objects. Originally we had planned it for 10. We also trained a binary classifier rather than an m-ary classifier because we only have these 2 objects available. So we used SVM, which is support vector machines. We also showed a proof of concept which pre-processing step works most efficiently for future work and researchers. And we also demonstrated how we can compute distance and angle from the current data. But we don't have actual ground truth to verify that these results, we can't cross-reference our results because of our lack of access to the lab. So the millimeter wave sensors, I'm going to give a brief overview of what they are and how they work here. So they're a MIMO sensor, which means that they're a multiple input, multiple output sensor. We have the TX antenna, which is a transmitting end, and this transmits chirp signals, which are sinusoidal waves that have increasing frequency linearly with time. And the chirp is reflected off of the object and received at the RX, or the receiving antenna. And this data here will have information on distance, velocity, and angle. Here we have the computations that entail from this. First, we have the distance measured in meters. given with this formula, where c is the speed of light, f is the frequency of the signal calculated through the bin number of the FFT, s is the slope of the chirp signal, and we also have the angle, theta, measured in degrees with the given formula, where lambda is the wavelength, omega is the phase difference, and d is the distance that we just calculated previously. So the preliminary results that we got, we trained, as I mentioned before, a binary classifier of two different boxes, where one was covered with aluminum and the other one was a cardboard box filled with random items. Our goal here was to determine which pre-processing step had the best testing accuracy, and the different ones we compared were Doppler fast Fourier transform, angle fast Fourier transform, and the Doppler and angle, both of them at once. So below are some images of what we got from doing this data collection. So this might not make sense at first. Let's further explore results and what this actually means. So using just the Doppler fast Fourier transform, we had a classification accuracy of 85%. Likewise, also with the angle fast Fourier transform, we had 85% accuracy, but when using both methods, we had a jump to 90% accuracy. So this received the best results, but as one might expect, using both of them at once can be computationally expensive as we increase the number of data samples, where we do want to use more data samples. That just wasn't the case here because we didn't have access to that. But in a normal situation, we will definitely be seeing a computational jump. So we were able to compute distance and angles, but we didn't have ground truth to compare. We can only, guesstimate, sort of, because of lack of access to the AB. So the computed distance was 2.5 feet, and we estimate that the object was approximately 2 to 3 feet away, based on our, given time in the lab. So conclusion and future work. Our original plan was to do object classification and imaging, but that classification meaning emery classification, but we were forced to switch over to binary object classification. We did observe what type of pre-processing steps were best for this classification for future work, and future work would involve collecting more data because we did not get a lot of data here, and we'd also be able to train a one versus all classifier. Additionally, we want to verify the distance, the accuracy of the distance, and the angle with the ground truth in the future. I want to thank you all for listening to this. Again, the team members here involved are Pradyumna Rao, Suman Kwan, Thomas Tran, and Matthew Varghese. Thank you.